trig integrals, we have two types of cases, as mentioned in the instructional. We have either odd powers or we have even powers. So the key is, I do want you to make a note of this. Identify whether the trig integral has an odd power. If even one of the functions has odd power, then we apply the odd power trig integral steps. Otherwise, if they're all even powers, then we apply the even power trig. So in this case, sine cubed, that's an odd power, so we're going to apply the odd power trig integral steps. So when we do that, we have to use the Pythagorean identities. But when we do even powers, we do something else. I have a video just on even powers as well. But when we're doing odd powers, we must use the Pythagorean identities. So without further ado, for step one, we're going to break down the exponent of the function. So we have sine cubed x times dx, and when we break this down, we get sine squared times sine x times dx. So basically when we break it down, what do I mean? I mean have the highest possible even power times 1, basically. So the highest, notice how I did not break it down into sine of x times sine of x times sine of x. I want to make sure I have one even power. Why? The highest even power possible, so I can apply the Pythagorean identity. So for step 2, since one of the functions has an odd exponent, we're going to apply the Pythagorean identities. So the Pythagorean identities, we know sine squared plus cosine squared is equal to 1. And we know that 1 minus cosine of squared is equal to sine squared x. So this was our function, sine squared x times sine of x times dx. So what we can do is we're going to move forward to step 3. We're going to go ahead and substitute in the Pythagorean identity in the place of sine squared x. We had sine squared, so we're going to substitute 1 minus cosine squared x times the sine squared x that we already have times dx. And now we're going to integrate this function. So we're going to do this by applying the u substitution. So whichever one for u substitution we select as u, whichever one has the highest power. So in this case, cosine squared x has the higher power than sine of x. So we're going to go ahead and apply u substitution, and our u is going to be cosine of x. So since our u is cosine of x, the derivative du is equal to negative sine of x times dx. And the dx, when we solve for dx, is du divided by negative sine of x. So now we're going to put brackets around this because we're going to substitute the u and the dx back into the formula. So in doing so, we're going to substitute dx into the integral, and we're also going to substitute in u. So in doing so, we get 1 minus u squared times du sine of x times du divided by negative sine of x. And in doing so, we know the sine of x cancels out, and that's the whole idea of u substitution. Is whenever we do the u substitution, we want to make sure that the terms will cancel out and we have everything in terms of just u. So now we're going to integrate this function with respect to u. So 1 minus u squared times du, and we know this will integrate to u cubed over 3 plus c. And when we do this, what we're going to do is we're going to substitute in the x terms, because now we have it in terms of u. We're going to substitute in the terms for x. So we know our u was equal to cosine of x. So our x is equal to cosine x. So we know u is cosine x minus cosine cubed x over 3 plus c. But one thing I did forget to do is notice right here I have a minus sign that I did not take into account. So the minus sign, you can actually include it at the very end, and it'll save you the trouble. Don't forget to include this minus sign. So this is actually the correct answer. So what we did basically was just apply u sub for the higher power, and then we cancel out the like terms. I factor out the minus sign, which I didn't do, but now I did it, so I corrected myself. And we know 1 minus u squared, and then we know u minus u cubed over 3 plus c. And then we substitute the x terms back in, and we get cosine of x minus cosine cubed x over 3 with the minus sign in front of it plus c. And this is about as far as you have to take it, so that's the answer to this problem. But what about something a little bit more complicated? So now in this example, we're given cosine of x times sine to the 5th power x. So make sure you make note of the note that I have there. Identify whether the trig integrals has an odd power. If even one of them has an odd power, then we apply the odd power trig integral steps. Otherwise, if they're all even powers, then we apply the even power. But in this case, it's odd power. So cosine of x times sine raised to the 5th power. So what we're going to do is we're going to break down the higher exponent. So we have sine of 5x. We can break it down to the highest even power possible is sine to the 4x times sine of x times cosine of x times dx. So now what I'm going to do is I'm going to break this down even further. I'm going to break down the sine of 4x as sine squared x times sine squared x times sine of x times cosine of x times dx. And of course I know that the sine of 4x is going to these terms right here. So the sine of 4x was broken down to those two sine of x terms. So for step 2, where since there's at least one odd power, we're going to apply that Pythagorean identity substitution. And that's what makes odd powers different from even powers. For even powers, we do power reducing formulas, which is in another video. But for this video, we're going to apply the Pythagorean identity since they're odd powers. So we know the Pythagorean identity. We know sine squared plus cosine squared is equal to 1. So when we solve this for sine squared, we know 1 minus cosine squared is equal to sine squared x. So we're going to substitute this in. So for sine squared, we're going to substitute 1 minus cosine squared x. And we're going to do it twice since there's two of these terms. And we're left with our sine of x and our cosine of x and our dx. Now we have it with the Pythagorean identity. It's already substituted in, as we do right here. Now we're going to go ahead and apply the u substitution to integrate this function. So in order to do this, we need to make a note that we're going to select our u as a term with the highest exponent. So our u, what's the highest exponent now? It's cosine. It's no longer sine, it's cosine. So our u is equal to cosine of x. Our du, the derivative of cosine, is negative sine of x. And times dx, and dx would be equal to du divided by negative sine of x. So now we're going to substitute the u and the dx into the integral, just applying regular u substitution. So we have 1 minus cosine squared x, 1 minus cosine squared x, sine of x, cosine of x, and then we have dx. So now we're going to substitute in all the u terms. So recall that our cosine is now u, so we have 1 minus u squared, and we have it twice, 1 minus u squared. We have times sine of x times u, because that's cosine, times du over negative sine of x. What we do here is we're going to cancel out those sine of x and factor out the negative. Now we're going to simplify this using algebra, so we can factor out a negative 1 because the denominator of the du was negative sine. We know the sines canceled out, and our cosine is u, so we have 1 minus u squared, 1 minus u squared times du. So we have everything in terms of u, but we have to simplify this. So the first thing we're going to do is we're going to FOIL out the two negative or 1 minus u squared. So 1 minus u squared minus u squared plus u to the 4th times du, and all I did there was just FOIL out. So I FOILed out the two terms that are inside the parentheses. And now I'm going to distribute the u to each term. So I know u times 1 is u. And first thing I'm going to do is notice how these two terms where my mouse is have this are the like terms, so I can simplify that to 1 minus 2u squared plus u to the 4th power times du. So now what I'm going to do is I'm going to distribute the u out. So I know u times 1 is u minus 2u cubed minus plus u to the 5th power times du. So now that I have everything in terms of u, I'm going to integrate this function with respect to u, since we have everything in terms of u and we are integrating with du. In doing so, when I integrate this function, I get the first term. When I integrate it, we're going to separate it into 3 separate integrals, so that way I don't mess up. And notice how I have separate parentheses. I have the negative 1 on the outside, so I don't get any sign convention off. So the u times du minus 2u cubed times du. All I'm doing is factoring out the constants plus u to the 5th power times du. So I'm going to integrate each term separately, and when I do that, when I integrate the first term in the orange brackets, I get u squared over 2. When I integrate the second term in the green brackets, u cubed is u to the 4th power over 4 times the 2 constant that's right in front of it. And when I integrate what's in the blue parentheses, u to the 5th is u to the 6th power over 6, and of course plus c. But we're not done yet because we have it in terms of u, so we need to plug in the u value from the u substitution. So our u is equal to cosine x, if you recall. So we're going to plug in, everywhere we see u, we're going to plug in cosine of x. So we have -1 still on the outside. We have plus cosine squared x over 2 minus cosine of the 4x over 2. Why is it over 2? Well, because 2 divided by 4 is 1 over 2, so I simplified that. Plus cosine of 6x over 6. And now what I'm going to do is plus c, because this is an indefinite integral. So now what I'm going to do is I'm going to distribute the -1 to each term. So in doing that, when I distribute -1, the only thing that's going to happen is the signs are going to flip. So our final answer is cosine of 4x over 2, and I'm putting these in descending order, minus cosine of 6, minus cosine squared over 2, plus cosine of 6x over 6, plus c. And that's the answer to this problem. So yeah, the key is right here is to apply the Pythagorean identity substitutions, because these are odd power, not even power. So now in this example, this one's a little different than what we've done already in the past. So we have secant cubed times tan to the 5th x. So what we're going to go ahead and do is, if you haven't observed the note, just observe it. I'm not going to repeat it. But these are odd powers, so since these are odd powers, we apply Pythagorean identity. We apply that for odd power trig integrals. So the first thing we're going to do is we're going to break down the exponent of the function. So we have secant cubed x times tangent to the 5th x times dx. That's our original function. And what we're going to go ahead and do is we're going to break down each term to its highest even power possible. So secant squared x times secant times tangent to the 4th power times tangent x times dx. And I'm just going to leave a little track so you know exactly what's being broken down into what. Furthermore, I can break down the tangent to the 4th power. So we have secant squared x times secant x. And we're going to break down the tangent to the 4th power as tangent squared times tangent x times dx. So if you follow that path, that's just me breaking down the exponent of the function. So now what I'm going to do in step 2 is I'm going to apply the Pythagorean identity substitution, since there's at least one odd power in this. In this case there's two, but since there's at least one of these as odd power, I'm going to apply the odd power Pythagorean identity substitution. So which one would be proper to use in this one? So we have secant squared and we have tangent squared. So I think that's the one we should focus on. So we know 1 plus tan squared theta as given in the table. 1 plus tangent x is equal to secant squared x. So for substitution purposes, we know that tangent x is equal to secant squared minus 1. And why am I selecting tangent x as a substitution? Because it's the one that has the highest power, because tangent's to the 5th power and secant's to the 3rd power. So I'm selecting tangent as the substitution that I'm going to select, so I can have everything in terms of secant squared. So now I'm going to have secant squared x times secant x times the tangent x that's by itself, and then for the 2 tangent squared x, I'm going to apply the substitution. So I have secant squared x minus 1, and then I have it secant squared x minus 1 because it's the higher power, times dx. This part of the problem, this is as far as we got so far, so we decomposed it, we applied the Pythagorean identity substitutions, and what we have now is we have the secant squared minus 1 in the place of where the tangent squared was. So what we're going to do now is we're going to go ahead and apply u substitution, because u substitution works so well for trig integrals. So we're going to go ahead and do that. So what's our u? Well, our u should be whichever one's the highest power on the current integral. So in this case, it's secant squared, so it would make sense to have secant squared as our integral. So as our u term, because it has the highest power as of right now at the where the current integral is. So select the term with the higher exponent. So easily our secant will be our u. So our u is equal to secant x, so which means our du, the derivative of secant x, is secant x times tangent x times dx. And when we solve for dx, we get du divided by secant x times tangent x. So now what I'm going to do is I'm going to go ahead and substitute the u and the dx back into the integral. So that's why I put brackets around them. It's because I'm going to substitute them back in. So our secant squared x times secant times tangent x times secant squared x minus 1 times secant squared x minus 1 times dx. So now right here I'm going to do the substitution. So just try to follow along. So u squared times u squared minus 1 times u squared minus 1 times secant x times tangent x times dx. Du over secant x times tangent x. So how did I decide that? Well, just follow the arrows as of right now. So this one goes here, this secant squared x goes here, this secant squared x goes here, because remember our secant is u, so I'm plugging the u back in. Our dx goes over there, and what we're left with is secant tangent. Secant tangent times secant tangent. So notice how I did not use u for that secant tangent. Why did I not do that? Well, I decided not to do that because I saw that whenever the derivative of secant was secant times tangent, I saw that they were going to nicely cancel each other out. So you can perfectly not take that secant that's by itself as a u term if you see that the derivative is going to cancel itself out. So that's why I decided to not do that, so that way I could see it cancel out. But just follow the arrows, so that way you know exactly which term was being placed where in terms of substitution. So now let's integrate this. What we're going to do is we're going to simplify this using algebra. So we know that what we have right now currently is u squared minus 1, u squared minus 1 times du. Because the secant tangent times tangent squared tangent canceled itself out. So the first thing we're going to do is we're going to go ahead and FOIL those last two terms. So we know u squared minus 1 times u squared minus 1 is u to the fourth minus u squared plus 1 times du. And we're going to simplify this a step further because u squared is equal to u to the fourth. And those two middle terms are like terms because they both are to the same degree. So this is minus 2u squared plus 1 times du. And now what we're going to do is we're going to distribute out the u squared to each term. So u squared times u to the 6th, since they have the same base, we can add the exponents. So it's 4 plus 2, so it would be u to the 6th power minus u to the 4th, 2u to the 4th power plus u squared times du. So now what I'm going to do is I can integrate this function with respect to u. So in doing so, I'm going to integrate this function right here. So the integral of u to the 6th times du minus 2u to the 4th times du minus u plus u squared times du. So all I did was just separate the integral into 3 separate integrals, and I do this method so that way it prevents me from making errors. So when I integrate this function, I get u to the 7th over 7 minus 2 u to the 5th over 5 plus u cubed over 3. So now what I'm going to do is plus c, of course, don't forget your plus c. So now what I'm going to do is I'm going to plug in u from the u substitution. So keep in mind that u from the u substitution was secant x. So thus our answer comes out to be positive 7 secant to the 7th power over 7 minus 2 over 5 secant to the 5th power plus secant cubed x over 3 plus c. And that's the answer. So again, these trig odd power integrals, we apply the Pythagorean identity substitution. If we have even power, we do power reducing formula, which I have that in another video. And if you see this content helpful, feel free to like, share, subscribe, comment, leave feedback. And I have a whole playlist on this and other classes as well. Thank you for watching. I hope this was helpful.